Step into the depths of the ocean where a daring expedition to explore the secrets of the Titanic's remains took a catastrophic turn. On June 19th, an expedition was launched to explore the mysteries hidden beneath the waves of the northwestern Atlantic. The Oceangate Submersible was tasked with descending into the ocean depths at a rate of 55 meters per minute. As it went deeper, it faced a significant challenge in the form of immense pressure. The submersible hull battled against the forces that threatened to crush even the most vital structures. At a depth of 3,800 meters, the submersible would be subjected to the weight of 366 Earth atmospheres. To avoid any confusion, let's make sure we all have a clear understanding of the definition of implosion. It's when something caves in on itself. Unlike an explosion that expands outward, the Titan submersible violently imploded within a fraction of a millisecond due to the immense hydrostatic pressure of the water surrounding it. Through an authentic communication transcript between the submersible and its surface support vessel, we can retrace the heart-pounding moments that unfolded during this unimaginable disaster. Join us as we navigate through the pages of this transcript, peering into the haunting exchanges that took place in the depths. Before we dive into the details, let's examine the distinctions between a submersible and a submarine. A submersible, typically people launch it from a larger vessel called a mothership or home vessel. It is placed on a platform or raft and submerged in the water. In contrast, a submarine can dive underwater without needing external equipment and resurface using its buoyancy control system. Having understood the fundamental differences between a submersible and a submarine, let's shift our focus to a specific submersible, namely the Titan submersible, and closely examine its specifications. Despite its compact size, the Titan weighs 95.25 kilograms to 1,000 pounds. It measures approximately 22 feet long, equivalent to 6.7 meters. Additionally, the object measures about 9.2 feet in width, which is roughly 2.8 meters, and stands at a height of approximately 8.3 feet or 2.5 meters. To provide some context, imagine how small it compares to an average human. Comparing it to a small SUV helps visualize its dimensions. It's designed to withstand enormous water pressure at depths of up to 3,800 meters or roughly 1,467 feet below sea level. That's equivalent to the weight of the Eiffel Tower pressing down on it. This submersible is built to endure such conditions, with the hull believed to have been constructed to resist these extreme pressures. Let's examine Titan's design and functionality more closely. The submersible was designed in a cylindrical shape to allow for more passengers. It has the capacity to hold up to 5 individuals, consisting of 1 pilot and 4 passengers. However, the passengers have to sit on the floor during the journey due to limited space. And yes, there is a toilet on board the submersible, separated from the rest of the capsule by a privacy curtain at the front. The pilot maneuvers the vessel using the joystick, propelling it forward, backward, or making turns as necessary. And 2 monitors provide essential visual feedback. The interior design of Titan emphasizes simplicity and functionality, considering the confined space available, and a carbon fiber tube was inserted between 2 titanium end caps. This carbon fiber is incredibly tough, used in the construction of airplane wings and racing cars. But does it possess both strength and suitability for submersibles as well? Make sure to watch the entire video until the end. In the final segment, I will reveal the defects and the events leading to the catastrophic failure. The process begins with the mothership, known as the Polar Prince, anchoring at a designated spot near the Titanic shipwreck. A ramp attached to the mothership is lowered, allowing the Titan submersible to descend slowly into the water. Once it reaches the desired depth, the submersible disengages from the platform and commences its exploration journey. The Titan's propulsion system is designed to navigate the challenging underwater environment, and the submersible is equipped with 4 electric thrusters that are essential for steering. 2 thrusters are horizontally, while the other 2 are vertically on either vessel's side. Impressive speeds of up to 4,000 meters (13,000 feet) can be reached, with speeds of 3 to 4 knots, equivalent to 312 miles per hour, achieved despite the high pressure and density of the deep sea. The rear of the submersible contains electronic equipment, including oxygen and navigation systems. Moreover, this unmanned vessel section can recycle carbon dioxide and generate oxygen for the cabin, providing a 96-hour oxygen supply. However, the Titan's journey to the Titanic was marked by tragedy. During a descent into the Titanic wreck, contact was lost with the submersible. It was later concluded that the Titan suffered a catastrophic implosion, a violent collapse inwards due to the weakened carbon fiber hull, which tragically resulted in the loss of all 5 passengers on board. Based on the information I found, the critical design aspect of Oceangate's Titan submersible was its composite hull made of titanium. End caps and composites consist of fibers bound together by a matrix material such as epoxy, resulting in variations in fiber orientation and the presence of voids or unfilled areas. While software simulations can help analyze specific failure modes, real-world testing is essential to validate and refine these models. Oceangate's reliance solely on computer modeling without comprehensive physical testing. Furthermore, Oceangate's decision to cure the composite hull without utilizing an autoclave, a pressurized oven that helps eliminate voids in the epoxy resin, raises concerns about the presence of porosity and defects. While Spencer Composites, the manufacturer commissioned for the hull, claimed that the porosity was assessed to be less than 1%, the lack of specific information regarding the actual porosity level leaves room for doubt. Despite these potential issues, the Titan submersible was unlike traditional submarines made of steel or titanium. The Titan's submersible utilized experimental materials, mainly carbon fibers. These carbon fibers are lighter than titanium or steel. Carbon fiber composites are best known for their strength and tension, making them suitable for applications such as pressurized aircraft fuselages. In such cases, the pressure inside the fuselage works to expand the circular cross-section, putting the fibers in tension. However, in a submarine, the pressure would act to compress the hull, subjecting the fibers primarily to compressive forces. Yet the use of carbon fibers in such a high-pressure environment is not without its risks, and their behavior under extreme pressure still needs to be fully understood. The carbon fiber hull can suddenly crack or break, leading to structural failure under high-pressure conditions. Then Rush justified the use of carbon fiber by stating that it is 3 times better than titanium in terms of strength to buoyancy, which is crucial when underwater. Neutrally buoyant submarines like the Titan aim to displace water with a weight equal to their own, minimizing the energy required for vertical movement. The lighter weight of the carbon fiber composite helps achieve this neutral buoyancy target. However, the decision to forego the foam outer layers typically used in submarine hulls to achieve buoyancy raised further concerns, so the manufacturing process needs to be carefully monitored to prevent any catastrophic failures. The Titan submersible did not use foam outer layers typically used in submarine hulls, but according to Oceangate's CEO Stockton Rush, the decision to skip the foam layer was driven by cost considerations. While cost optimization is not inherently problematic, it becomes questionable when the structural integrity of the composite is uncertain. Oceangate's justification for not subjecting their submersible to testing by a regulatory body further adds to the doubts surrounding their engineering decisions. Instead, it used a carbon fiber cylinder, a problematic structure that was developed in collaboration with Boeing. The domes of the Titan submersible were made of 3¼ inch thick titanium, with a carbon fiber face and interface glued together. Concerns were raised about the absence of thorough testing and certification procedures, with the carbon fiber used being past its shelf life. Warnings were overlooked, and the lack of third-party scrutiny of the vessel during development could have caused catastrophic safety problems. Despite the acoustic monitoring system, the submersible suffered an implosion due to its weakened carbon fiber hull, which experienced more external pressure due to its design. The material wear and tear of the Titan's hull, a 5-inch thick structure subjected to repeated stress for about 24 previous dives, may have caused tiny cracks to form in the structure, leading to its rapid and uncontrollable collapse. Non-destructive testing methods like ultrasonic scans were recommended, but Oceangate criticized the third-party certification process as time-consuming and stifling innovation. The Titan was descending too quickly, with its reported depths consistently exceeding expected depths. Alarmingly, they were close to the Titanic shipwreck much earlier than anticipated, suggesting a serious problem with the sub's speed and descent. Oceangate's decision to use carbon fiber for the Titan submersible instead of traditional materials like steel or titanium was a risky gamble due to its potential for catastrophic failure under pressure. The last few entries from the Polar Prince indicate crew awareness of the issues they were facing, but lack of communication from the submersible in the final moments reveals the tragedy of the event.